stop and think about how all those little computers inside your phone or your laptop or even your car actually talk to each other? Well, for any conversation to work, everyone has to speak the same language. And in the world of electronics, these languages are called communication protocols. So today, we're going to break down the essential roles that let our devices work together seamlessly. So to get started, you got to know that data can be sent in two main ways. Over on the left, you've got parallel communication. Think of it like a massive 8-lane highway where all 8 bits of data show up at the exact same time. It's super fast, sure, but it needs a ton of wires. Now look to the right. That's serial communication. It's more like a single-lane road where each bit has to follow the one in front of it. Now you might think that sounds slower, but its simplicity and low cost, that's what makes it so incredibly powerful, especially when you need to send data over longer distances. Okay, so let's put a real definition to it. Serial communication is quite simply the process of sending data one bit at a time in a sequence over just one single channel. This is literally the backbone of how countless devices communicate. And why? Because using fewer wires means lower hardware costs, and it's also less likely to pick up interference or noise. That's why it's the go-to method for pretty much everything, from tiny microcontrollers all the way up to complex scientific instruments. So here's what we've got on tap. First, we'll get into the core idea of sending data one bit at a time and look at how devices stay in sync. Then we'll break down 3 of the most common protocols out there: UART, SPI, and I2C. And to wrap it all up, we'll put them side by side to help you figure out which one is the right tool for the job. All right, section 1, one bit at a time. So think about this. If you're sending a stream of bits, one by one, down a single wire, how on earth does the device on the other end know when one bit stops and the next one starts? It's a huge timing problem, and there are 2 main ways to solve it: synchronous and asynchronous communication. So this slide really shows you the 2 different philosophies for keeping time. Asynchronous, over on the left, is kind of like sending a letter. You add a special start bit at the beginning of your message and a stop bit at the end. The receiver just has to know the speed you agreed on beforehand. That's called the baud rate, which you can just think of as bits per second. Now, synchronous, on the right, is more like having a conductor with a metronome. Both devices share a clock signal, which is just a steady pulse that tells the receiver exactly when to look at the data line. It's way more precise, but it means you need an extra wire just for that clock. Let's move on to our first protocol and see how this all comes together. Section 2, the simplest talk, UART. This is probably one of the most straightforward and common ways for 2 devices to have a direct conversation. So what even is UART? It stands for Universal Asynchronous Receiver/Transmitter. And you should notice that key word right away. This protocol uses that asynchronous method we just talked about. It's basically a piece of hardware that takes parallel data from a device's brain, its CPU, and translates it into a serial stream to send out, and it does the reverse for incoming data. It's a simple, direct, peer-to-peer system. And this image just shows you the beautiful simplicity of UART. You've got 2 devices. The transmitter pin, or TX, of the first device connects to the receiver pin, or RX, of the second one. Then, the TX of the second device connects to the RX of the first. This little crossover creates a direct 2-way street, which means they can both talk and listen at the very same time. We call that full duplex communication. So what are the trade-offs here? Well, on the plus side, it's super simple. Just 2 wires, no clock signal needed. It even has an optional parity bit, which is a basic way to check if any of the data got messed up during transmission. But the downsides are pretty big. It can only connect 2 devices, period. Like a GPS module talking to a microcontroller. Also, the amount of data you can send at once is limited, and both devices have to be set to the exact same speed, or baud rate. Otherwise, the communication just fails. Okay, but what if you need more than just 2 devices to talk? Well, that brings us to our next section. Section 3, SPI. This protocol introduces a much more organized system, almost like an orchestra conductor leading a group of musicians. SPI stands for Serial Peripheral Interface. And notice this one is a synchronous protocol, so we're back to using a shared clock signal. In this setup, one device is designated as the leader. It controls the clock and starts all the communication. The other devices are the followers, and they only speak when spoken to. Now, it's really important to know that you'll still see the older terms master and slave all over the place in documentation. The industry is definitely moving towards more inclusive language like leader, follower, or primary, secondary, because the concept is just about one device coordinating the others, not about ownership. And this slide really shows off SPI's flexibility. On the left, you've got a simple one-to-one connection. Easy enough. But on the right, that's where you see its real power. One leader device can talk to multiple follower devices. And how does it do that? By using a separate slave select or chip select line for each one. Think of it like an old school phone switchboard. To talk to the SD card reader, the leader pulls its select line low. To talk to the display, it pulls that line low instead. And that's how a single microcontroller can manage a whole bunch of different components. SPI's biggest advantage is definitely speed. It's way faster than UART, and you can just stream data continuously without breaking it into little pockets. But the trade-off is in the wiring and the protocol itself. Every new follower needs its own select line, so the number of wires can add up fast. And maybe more importantly, SPI is kind of like shouting into the void. There's no built-in confirmation or acknowledgement that the follower actually received the data correctly. You just have to hope it got there. So, we've seen a simple 2-way chat with UART and a one-to-many system with SPI. But what if you want to connect a whole bunch of devices with the absolute fewest wires possible? Well, that brings us to section 4, the two-wire bus, I2C. You can think of this as a party line where lots of different devices can all listen in and talk. And this is the central puzzle that I2C solves, right? If SPI needs an extra wire for every single new device, but you've only got 2 wires to work with, how could you possibly manage a whole network of sensors and chips without it all just turning into total chaos? The answer is so elegantly simple, and it's a complete game changer. Instead of using a physical wire to pick which device you're talking to, you just give every single device on the network its own unique digital address. The leader doesn't flip a physical switch, it just broadcasts a message that starts with something like, "Hey, device number 7, this next message is for you." I2C, which we pronounce I squared C, stands for Inter-Integrated Circuit. It's a synchronous bus, so yep, it uses a clock. But here is the magic trick. It only needs 2 wires for everything: a serial data line, or SDA, and a serial clock line, SCL. And what's really incredible is that it also supports multiple leaders and multiple followers all sharing those exact same 2 wires. This diagram shows that party line idea perfectly. You've got a microcontroller, which is usually the leader, and several follower devices like a temperature sensor or a pressure sensor, and they are all hooked up to the exact same SCL and SDA lines. When the leader wants to talk to one of them, it broadcasts that device's unique address onto the data line. All the other devices see the address, realize it's not for them, and just ignore it. But the one with the matching address, it wakes up and gets ready to respond. The advantages of I2C are just huge. You only need 2 wires, no matter how many devices you add. It can support multiple leaders, and unlike SPI, it has a built-in acknowledgement bit, so the sender actually gets confirmation that the message was received. The main drawback? It's just slower than SPI. Because data and acknowledgements have to share that single line, devices can't talk and listen at the exact same time, which makes it half duplex. The hardware and software to handle all that addressing logic is also a little more complex. Okay, that was a ton of information. We've covered the simple one, the fast one, and the super flexible one. So let's bring it all together in our final section, choosing your protocol. This chart really puts the core trade-offs right next to each other so you can see it all at a glance. UART is your simple, 2-way direct line, but it's also the slowest by far. I2C is your minimalist party line, great for managing lots of devices on just 2 wires at pretty good speeds. And SPI is the speed demon. It's blazing fast and full duplex, but you're going to need more wires and it has less built-in error checking. The key takeaway here is that there's no single best protocol. The right choice is always a trade-off between speed, how many devices you need, and how simple you want the wiring to be. So we'll leave you with this thought. The next time you plug in a USB mouse or check the weather on your phone or even start your car, just remember these invisible conversations are happening all the time, all around you. Each one is based on a choice, a trade-off between speed, simplicity, and scale. And now that you know the languages they speak, you can start to see which protocol is at work.
Thanks for watching. Please visit the channel for such more content, and don't forget to subscribe the channel and like if it is helpful to your knowledge, and comment if something is wrong.